All right, so we introduced the idea of a Fourier transform, or what we call a frequency spectrum. All right, what this basically says is if I've got a periodic waveform x of t, that periodic waveform always has, we said, a Fourier series. And we had three different ways of expressing that Fourier series, but we said the most common way was typically to use this complex exponential form of the series. Okay. Now, remember that because these complex exponentials, if they run from negative infinity to positive infinity, it's always going to be the case with this that if I looked at, let's say, n equal to 1, this would mean that I would have alpha 1 e to the j omega naught t, and there would also be an n equal minus 1 term that is alpha minus 1 e to the negative j omega naught t. And what we've said before is using Euler's identity, I can always turn this into 2 magnitude alpha 1 cosine omega naught t plus whatever the angle of alpha 1 is. Okay, so there was the Fourier series says that this waveform x of t, which is periodic, can be written as a sum of cosine waveforms, okay, that are harmonically related, meaning their frequencies are integer harmonics of each other or integer multiples of each other. Now, if that waveform is periodic, then we say it also has a Fourier transform or frequency spectrum, which is defined by this equation here, which in words basically says that what I do is I take those alpha n values and I use them to denote how much energy there is at each particular frequency in that waveform. Okay, and we're going to look at examples of this. But what we want to do with this is we want to create a graphic that looked like what I showed in class, which is to say if I have some periodic waveform of some kind, like this thing that I show here, I want to be able to express, well, what are the amplitudes at the individual frequencies? That becomes really important from an analysis perspective, which we'll talk about later. Okay, all right, so if we want to find this Fourier transform or frequency spectrum for this periodic waveform, there's basically three steps for us to follow. Okay, the first step is because the Fourier transform needs these alpha n values, the first step is to find the Fourier series coefficients alpha n. Now the second step is to basically take those alpha n and map them to the frequencies that they belong with. Okay, so for instance, alpha 1 goes with the fundamental. Alpha 2 would go with the second harmonic, so on and so forth. All right. And then the third step is to basically then determine this x of omega in terms of this equation here, which basically is to say make x omega a sum of the impulses located at the appropriate frequencies. All right, so let's look at the same example that we looked at in class. Let's look at this a little bit more slowly again. All right, so step one, let's determine the Fourier series coefficients alpha n. Now in this case, I've been given the waveform, so I don't need to determine the alpha n's by doing calculus. I can just kind of look at the waveform and manipulate it. And because I'm given waveforms in sort of the cosine and sine format, what I can do is I can just use Euler's identity, which I've written here for myself. All right. And I can use Euler's identity to get that into the complex form of the series that we have right here. Okay. So we'll begin with that. Now, the simple thing to do is probably to start with number 5 right here, right? So what I see here is that for n equal to 0, right? I know that this is n equal to 0 because this corresponds to the DC term, okay? So in other words, this guy is for omega equal to 0. For this, I have alpha 0 equal to 5. That value is the DC offset of the waveform, okay? Now, what I also have here is cosine 2 pi 60t and sine 2 pi 180t. So what I see is that I have a fundamental here. I'm going to write this. Omega naught is the way I usually write my fundamental. That's 2 pi 60. Okay. All right. And then I also have n equal to, in this case, it looks like I have n equal to 3, which is an omega value equal to 3 omega naught, or 2 pi times 180. Okay. Now we need to determine what the alpha values are for those two. So we'll start with the easier one here, right? So I'll use my Euler's identity. That's the first term here. Okay. So when I start with the Euler's identity, I have 4. So 4 cosine of theta equals 4 over 2 e to the j theta plus 4 over 2 e to the minus j theta. And in this case, theta looks like it's 2 pi 60 t plus 60 degrees. Okay, plus 60 degrees. So that turns this into 4 over 2 e to the j 60 times e to the j 2 pi 60 t plus 4 over 2 e to the minus j 60 degrees times e to the negative j 2 pi 60 t. Okay, so I expanded out the fundamental or first harmonic term. So looking at this, I can see that what I have here is this guy is my alpha 1. This guy here is my alpha minus 1. Okay. And I need to do the same thing for the sine term. Now I wrote here, if I have a sine, I can always turn that into a cosine shifted by negative 90 degrees there. And so for n equal to 3, what I have is 6. I'll write it this way. 6 cosine of theta equals 6 over 2 e to the j theta plus 6 over 2 e to the minus j theta. Okay, I said I like doing it that way rather than trying to remember what the sine version of Euler's identity is. And in this case, I'll say my theta equals 2 pi 180 t minus 90 degrees. Okay, all right, so I'll say that this becomes 3 e to the negative j 90 degrees times e to the j 2 pi 180 t, okay, plus 3e to the j 90 times e to the negative j 2 pi 180 t, okay? So remember this one's negative. All right, so the first term I wrote here is for the positive going vector, so I'll call that alpha 3, and this guy is alpha minus 3. So what I've determined here is if I look at my alpha n, in this case, my alpha n should have, just so that we're totally clear on this, my alpha n values should be 3 e to the minus j, sorry, I'm going to start from n equal to 3. Okay, start from n equal to 3. And that gives this, or sorry, I'm going to start from n equal to minus 3. Okay, n equal to minus 3. I have 3 e to the j 90. Okay, and then at n equal to 2, well, we didn't have a second harmonic, so I'm going to set that to 0. Or n equal to minus 2, sorry. Then I'm going to go n equal to minus 1. At n equal to minus 1, it looks like I have, what, 2 e to the minus j 60 degrees. And then at n equal to 0, it looks like I have 5. That was my alpha 0 term. And then at n equal to 1, I have 2 e to the j 60 degrees. At n equal to 2, again, I don't have anything, so I'm going to set that to 0. And then at n equal to 3, I have 3 e to the j negative 90 degrees. Okay, so we've determined basically all of the non-zero coefficients that really matter to me. The rest of them aren't important. The rest of them are all zeros. Okay, all right, so that's the first step. We've determined the alpha n values that are relevant for this problem. Again, there's infinitely many, but the rest of them are 0. So now what we got to do is we got to say, all right, well, let's map those values to the appropriate frequencies. So on that last slide, we determined what the alpha n values were that we needed. So I'm going to write it this way. So for my n values and my omega values, let's see what we have. So basically we had -3, -2, -1, 0, 1, 2, 3. And again, there's many more, but those are the only ones that we sort of deem to be relevant. All right. So what I say is then that the signals, the cosines in these waveforms are harmonically related. There's integer multiples of each other. So the omega values are basically n times omega naught. Okay. So in this case, what I have is -3 omega naught, -2 omega naught, negative omega naught, 0, omega naught, 2 omega naught, and 3 omega naught. And remember, this term and this term combine to create a cosine at 3 omega naught. This term and this term combine to create a cosine at 2 omega naught. This one and this one create a cosine at omega naught, and this guy creates a DC term. All right. So if I were to create that in MATLAB, basically I would say, well, I want an omega vector that goes from negative, well, we'll come back to the MATLAB question later in this video. Okay. All right. The thing I want to remember here is I want to relate the alpha n values to those frequencies. And so what I'm saying is alpha -3 goes with the term at 3 omega naught. Alpha -2 goes with the term at 2 omega naught. Alpha -1 goes with this guy. Alpha 0 goes with this guy. Alpha 1 goes with this guy. Alpha 2 goes with this guy. Alpha 3 goes with this guy. And I don't want to repeat them here. You can go back to the previous slide earlier in the video to see that. Now what I need to do is I need to determine the x of omega as a sum of impulses located at the appropriate frequencies, right? So x of omega was, again, by definition, as n goes from -infinity to infinity, alpha n delta of n minus, delta of omega minus n omega naught. Okay, so based on what we just wrote over here, right, based on the frequencies that we've got here, all right, what we need to do is to figure out where we're going to put those impulses. So let me see if I can I do this? I'm going to copy this table over. There we go. Copy this table over and go back to my full screen mode. Okay. So what I'm going to do is I'm going to say, I'm going to relate these guys here to impulses. Okay. Omega minus n omega naught. So do this slowly, right? So that means I have alpha 3 times delta of omega plus 3 omega naught. Now notice it became a plus because this is written as minus, right? So the omega value that I'm talking about is minus 3 omega naught because this is for n equal to -3. So that means that this becomes a plus sign, okay? Which means, start drawing a graph over here, right? That means that, and remember we said these alpha values are complex. So I'm going to draw the magnitude of the alpha values, okay? We talked about that in class. This guy is complex, so I need to plot the magnitude and the angle separately. All right, so here at -3 omega naught, we're going to have an impulse that has a magnitude like that, okay? The next one here is going to be, right, that's alpha -3, sorry. So then alpha -2 delta of omega plus 2 omega naught, okay? Again, plus because this is minus and this is minus. So 2 omega naught would be here. Now in this particular case, I don't have a term at -2 omega naught, okay? Then alpha -1, that impulse is going to be at plus omega naught. Again, minus and minus. So in this case, amplitude-wise, what were the actual amplitudes? This guy's a little bit smaller. Okay. So this guy is going to be here, and he's about half or 2/3 the size, I guess, of this one. Okay. At negative omega naught. All right. And then we have alpha 0 times delta of omega, right? This guy is at n equal to 0, and he has a height of 5, okay, or an area of 5. Then we have alpha 1 delta of omega minus omega naught. That's going to be here at omega naught. And then we have alpha 2 times delta of omega minus 2 omega naught. That guy's going to be centered here. And of course, he has no height because the alpha 2 value is 0. Then I have alpha 3 times delta of omega plus, sorry, not plus, but minus 3 omega naught. And that's going to be here. So this is 3 omega naught. So at that point, I've drawn the magnitude of that Fourier transform. And then I would also need to do the angle, right? Which is to basically look at the angle that is included in each of these, okay? So for that, it's relatively easy to do it, but I'm not going to do it by hand here. I'm just going to jump to sort of doing it in MATLAB. So what I wanted to do here is I wanted to look at what I've drawn. So the way I specifically did this here in MATLAB is I defined for myself what my omega naught is, okay? And then I set up my omega vector. And in this particular case, I decided to plot it from minus 7 omega naught in steps of omega naught up to 7 omega naught. This guy's going to have to be symmetric, right? Because I need to have a negative, in the complex form of the series, I need to have a negative term and a positive term to match each other. That's the only way to really get the full cosine that exists in the real world. So what I did was I then created an alpha vector, and then I loaded up the appropriate values in the alpha vector, okay? And you can check my math and my locations to see where I came up with that. But the critical thing is what I did here to plot this is I used this subplot command. All right, it's subplot 2, 1, 1. What this does is it tells MATLAB that in figure 1, I want to have essentially 2 plots. I want to have, so it's saying I want my plots arranged so that there are 2 rows and 1 column. And in the first of the 2, I want to make this plot right here. Okay. Don't worry too much about the syntax of the subplot command. You'll probably only ever create 2 plots like I've done right here. All right. So what I've done is I've said stem and I've said omega abs alpha. What stem does is it basically creates impulses. Okay. And so what I've done is I've plotted in the top graph, in the top subplot, I've created the magnitude. And notice down here, I've created a second plot. So subplot 2, 1, 2, I did stem, omega, and then I did the angle, all right? And I multiplied by 180 over pi to convert that to degrees, okay? And there it is. There's my graph. The magnitude up at the top looks exactly like what I would expect it to do. And then at the bottom, I've got my angles, which also looks exactly like what I would expect to do if you go back and you look at my previous work. All right, that's it.